Lewis Bowen's Nova lectures, and he's going to actually just inform me he's giving the fourth lecture first. Third one will come on Monday. The next lecture will be on Monday at what time? I think it's at 3:30. No, 4:30.
Oh, yeah.
No. Anyway, it's announced. The final lecture will be, I think, on a Friday, just 2 weeks from today. So his title for today is Classification of Bernoulli shifts.
That's right.
Yeah.
Okay, thanks. Yeah, thanks again for the invitation. So, yeah, okay, yeah, as always, please ask questions when they come up. So I'd like to start by defining the problem that I'm interested in. So gamma will be a countable group, and I'll be interested in classifying actions of a countable group. So by actions, what I mean is I'll have a probability space, usually denoted x mu, and let's say, and all of my actions are going to be measure preserving. Okay, so I'm interested in classifying these kinds of actions. So what does it mean to classify? So we say that actions, so if we have two actions, they are isomorphic. Or you can also say measurably conjugate if there exists an isomorphism of measure spaces which intertwines the actions. Okay. Okay, I want to classify actions up to isomorphism, which is a very ambitious problem. In fact, it's known to be impossible. There are rigorous anti-classification theorems due to Benji Weiss and Matt Foreman. But I'm going to be looking at a very special class of systems, where we can say something interesting. And these are the Bernoulli shifts. Okay, so these are defined as follows. Sorry, what was the theorem you said? There are anti-classification theorems. So I'll tell you in a really, in a nutshell, one of the theorems. You can look at the group of all automorphisms of this measure space. And you can ask about classifying these up to measure conjugacy, which is the same thing as conjugacy within this group. And so what would it mean to classify? Well, you might think what we should have is a Borel way of assigning to automorphisms a countable graph in such a way that two automorphisms are measurably conjugate if and only if those countable graphs are isomorphic. And the theorem says that there is no such Borel way of assigning. There isn't a non-measurable way of doing it, just using the axiom of choice, but there is no Borel assignment. Okay, so any questions? Okay, so let's let K kappa be a probability space. And K kappa to the gamma is the product space. So this is just, you can think of this as just the set of all functions from gamma into K with the product measure. Okay. And the group, acts on this space by shifting. So one way of thinking about this is that these are like colorings of the group. and we're just moving the colors around.
K is a finite set. What's K?
K can be, this is just any probability space, but for intuition's sake, it's helpful just to think of K as a finite set, and that's already a very interesting case. That's the main case. And, okay, so these are called, this is the Bernoulli shift. Over gamma with base. So this K kappa is called the base space. So if we fix the group but we vary the base space, you can ask, well, which ones of these are isomorphic and which ones aren't? And so this is a basic problem that goes back to von Neumann in the 20s. He knew that all of these, he was just looking at the case when the group is the group of integers. But he knew that all of these are spectrally isomorphic. They're all isomorphic to the, well, if you look at the action of gamma on the L2 space of this, what you get is isomorphic to the action of gamma on the regular represent, on L2 of itself to the countable power. Okay, so the answer to this, the first step.
You looked at this in this generality?
Well, I don't think so. I think he was just looking at the integers. Yeah.
Because this is the spectral theory of even L2 of gamma for some weird regular representation is quite nasty. So it's not like you can compute that that easily.
Yeah, right. Yeah, I mean, he must have. Right. Well, so so I'm going to give you a little bit of review before getting into new things. So I'll be, the new material is going to be when gamma is a non-amenable group. That's going to be very interesting, especially when gamma is a free group. But I want to review some of the classical material, and it goes back to Kolmogorov and Sinai. So this is the Kolmogorov-Sinai entropy. Okay, so I'll just go over this review kind of quickly, but if you want, please. Please stop me and ask for more. So, okay, so T will just be an automorphism, so I'm just going to be looking at actions of the integers to begin. And I'll have a function from x to a, which is going to be a measurable function. A here is just any, let's say, a finite set for, to keep things nice and intuitive. Then the entropy rate, or the Shannon entropy, the Shannon entropy of this random variable is defined by this formula. And I guess if you're first seeing this for the first time, it might look very strange. But so I'll give you a little bit of intuition. Suppose that A is just let's say heads tails, and that the measure, when we push forward this measure, that we're just getting half-half. So it's just the uniform measure. In this special case, the entropy is just log 2. I like to take base 2, so this is log base 2 of 2, which is 1, so this is 1 bit. And in general, what this, informally what this is doing is measuring the amount of randomness in this random variable. And so one coin toss gets 1 bit of randomness, if you will, but really it's entropy. And if you had n coin tosses that were independent, then the answer would be n. Okay. Okay. So What's about the entropy rate? So this is just the entropy of a single random variable, but now we'll talk about the entropy per unit of time. So it's defined like this. We take the entropy that is in this random variable phi joined with its translates up to time n and divide by time n plus 1. So we're just getting the amount of randomness that's in this composite random variable. Is this everybody? Okay.
You can't. Make sure he's correct.
Okay, so intuitively what this is saying is if we, well, it turns out you can also write this as, well, you can think of this in the following sense. If you have some kind of physical system that's evolving in time, and phi is your measuring device. So every unit of time, you make a measurement and you're watching, so you're getting this, this data. Then after you've been watching it for a certain amount of, for a very, very, very long amount of time, you can ask how predictable is the next symbol. And this is giving you that answer in the number of coin tosses, So if the answer here is 1, then it's as predictable as a single coin toss. Okay, so this is called the Kolmogorov-Sinai entropy. And it has some very nice properties. So first of all, I need one more definition. The entropy of the transformation by itself is the sup over all phi. So we also let A here is just any finite set. Okay. Yes. Yeah, finite partition. I like to think of it, you can think of it as a partition just by pulling back the elements of A. Okay. So this is a measure conjugacy invariant. It's so these are and it has this very nice feature that when we apply it to a Bernoulli shift over the integers, what we get is the Shannon entropy of the base space, which by definition, this is the, I guess I didn't tell you what this is, but so this is the entropy of, you can think of it as the identity map from K to itself. I told you what the entropy of a random variable is, so the identity map here is a random variable. If you don't like that, you can just say it's this formula, right? It's a measure of, the kappa measure of A times log of the kappa measure here, and A here is in capital K. Okay, so this tells us that certain Bernoulli shifts are definitely different. If they have different, if the base spaces have different entropies, then they are different. There's one more fact that I'm going to need, which is that suppose that we have the following, that we have some measure space and we have some other probability space, and we have an automorphism T, and we have an automorphism S, and this square commutes. So in this case, that we call S a factor of T.
Projection.
Yes. Yeah. Okay, so it follows straight from the definitions that the entropy of S is at most the entropy of T. And this is very intuitive. A factor, you know, when we're looking at a factor, what we're doing is we're reducing the amount of randomness. It's like we're putting on blurry glasses, and so we're not seeing everything. Yeah. Okay. Okay, I'll get to new stuff soon, I promise. This is very standard. Okay. Yeah, any questions? Yeah, okay. Okay, so let's go to arbitrary groups now. So here, gamma is just going to be an arbitrary countable group. And if you look at this definition of entropy, you might think, here's a good idea. Let's suppose gamma acts on x mu. And we could define the entropy of this action in the following way. Preliminarily, it'll turn out that this is not a particularly, well, anyway, I don't want to give it all away. So preliminarily, what we might think of is, okay, we take, you know, we're going to have some what we're going to do is we're going to look at random variables from x to a. Now this W is a finite subset of the group. That's comparable to the set 0 to n here that we took. And so what this phi to the W is it's just this composite random variable where we take phi and we precompose it with elements from this finite set. So, for example, what I have over here, phi joined with phi composed with t, etc. This would be written as this would be written in this notation in this way. Okay, so we can just think, okay, well
Z, you sort of exhausted Z in this very clean way, where you ordered Z.
Yeah, that's right.
You didn't take sort of subsets of size n, which were sort of spaced or something. So, and here.
That's right, yeah. So here we don't have any order. You know, it's just an arbitrary group. So we don't have any particular preference. So we just take any finite subset and just move our random variable around by this finite subset, take its join, take the average, take the infimum over all finite subsets, and then we want to take the sup over all phi. It turns out that this works well sometimes. For Z, it turns out you get the same thing as before. So it turns out that if gamma is amenable, then this is a nice notion in that it satisfies all of the properties that we have already listed. 1, 2, and 3. Right, I guess I didn't write 3 up there, but. So it's a measure conjugacy invariant. It's obviously a measure conjugacy invariant, by the way, for anything. But it gives you the right value for Bernoulli shifts. And it's obviously monotone under factors. But when it's non-amenable, if gamma is non-amenable, there's a real problem. Because it turns out that this entropy is always 0 or infinity. And this is not a difficult calculation. This is a little exercise that you can do. You just say, well, suppose that, for some phi that this is positive, and then you just replace phi with phi to the W for some finite W, and you'll see that you can make it larger. And you can just keep on making it larger. So it's not going to distinguish Bernoulli shifts. Okay. Okay, so let me give you an even more problematic, another problem.
So in some of your applications, maybe your first lecture, I remember that just whether something was zero or infinity was enough to, on that one-to-oneness. You had this definition which used Benjamin Schramm, which probably will reappear here.
Yeah, at the end, yeah.
And then somehow you were saying, I'm just trying to understand the feature,
So
whether something, oh no, there was a notion of finite there, sorry. Okay, I take it back, yeah. Not zero, there were three possibilities.
Okay, so let me tell you something that's even more problematic in the sense that, you know, the first ideas that you might think of for extending entropy to non-amenable groups are going to fail. And so this will tell you why. The reason it has to do with number 3, that, you know, entropy is supposed to decrease under a factor map, or maybe stay the same. Fine. And it's also supposed to be, by number 2, it's supposed to give you this value for Bernoulli shifts. So what it tells you is that if you put k here, let's suppose you had the 2 shift. So the 2 shift is where k is just a 2-element set and kappa is the uniform measure. And the 4 shift is where k is a 4-element set and kappa is the uniform measure. So the 2 shift cannot factor onto the 4 shift, right? Because that would be, entropy would be increasing. That would be saying we have a coin at every vertex or every group element, just a random coin, and somehow we've mapped it onto having 2 random coins on every, right? That can't happen. But Ornstein and Weiss actually prove that that can happen when the group is the free group. So, okay. Okay, so here's the free group. It's just A and B. And they defined this map. Actually, I'd like to call this capital phi now, since lowercase phi is a random variable. Okay, so we're going from Z mod 2Z to the free group into Z mod 2Z times Z mod 2Z to the free group. And the map goes like this. So I need to tell you what it is on an element gamma. Let me show you what this is, because I think, you know, if you just see it in symbols, it's a little difficult to get. So the free group looks like this. You know, it's the Cayley graph. And what we have right now is just zeros and ones on every vertex. That's what we, you know, so maybe this is a 1 and this is a 0. Maybe this one is a 1. Maybe this one is a 0, etc. And what the map does, I'll just try to be speedy here, is it says, okay, take this one and add it to the one north of it. And take this one and add it to the one east of it. And just add mod 2. And we do that at every vertex. So this would be, you know, 1 and then whatever. And it's an easy exercise to check that what you get is, in fact, IID here. You know, that it is just uniform measure. In fact, you can think about it this way. This is a compact group under addition, and this is a compact group, and this is a homomorphism. And in fact, it's a surjective homomorphism. The kernel is just the constants, Z mod 2Z. So this is a 2-to-1 map. And, you know, 2-to-1 maps in classical entropy theory, they preserve entropy. In fact, any finite to 1 map preserves entropy. So this is considered to be very odd. And it convinced many people that there couldn't be any entropy theory. And so it was an open problem for a long time, you know, whether or not there could be any entropy theory for free groups. Or maybe all the Bernoulli shifts are isomorphic. one could imagine. Okay. So I want to explain, so I'm going to tell you that, well, I'll develop an entropy theory for free groups which distinguishes these two, so they are not isomorphic. But before getting there, I want to kind of give you some intuition about what the, how this entropy is developed. And so I want to go back to the integers first, and then we'll see how to generalize. And going back to the integers, it's kind of helpful to think about Markov chains. It's not completely necessary, but I think it kind of helps. So suppose we have a Markov chain or Markov process. So what it means is that we have an automorphism. And we have a random variable. X here is always a finite set, an alphabet. And it has the property that if we know the past, then the law of this random variable, or its probability distribution, conditioned on the past, is the same thing as its law, conditioned on the immediate past. Okay. And so this tells you that the entropy rate of this random variable is just the entropy of phi conditioned on the immediate past, which I didn't tell you what that is, so I'll do that now. You can, it's, okay, really that's a lemma, but that's what it is. Okay, with Markov chains, you can, well, I guess this formula is nice because it means that you don't have to compute any limit. You can just, it's just a finite calculation to compute the entropy. But every system can be approximated by Markov chains, and that's what makes them very useful for entropy theory.
There is even inverse statement. If you have this formula for the entropy, then it's not a chain.
Right. Yes. Yes, this is a characterization of Markov chains. Okay, we can also go, right. Oh, okay, so I wanted to say the following, that in general, so if we have a process that doesn't have to be Markov, we can write the entropy rate, well, in the following way. It's the entropy of phi joined with its translates over this interval, and then phi joined with its translates again composed with t, and we take a limit as n goes to infinity. This probably might not look very familiar, but it's equivalent to saying that it's the entropy of phi conditioned on its past, which is the more familiar way of writing this. Okay, so back to free groups. By the way, so for free groups, this gives us an idea, which is, okay, so let's say now gamma is the free group, A and B, and it acts on some space, and we have a random variable. Well, maybe this is a Markov chain over the free group, which one can make sense of that. I won't do it at the moment. Later on, I'll show you an example. I don't really need to make a rigorous definition because it's not going to play a big role. But okay, so what we might think of is the following. we're interested in taking phi conditioned on the immediate past. But there's two notions of past. There's a past in the A direction, and there's a past in the B direction. So we'll just add them. But now you realize that this is a little bit funny because it's like we've taken the entropy, in this direction and the entropy in this direction, but we've kind of counted the vertex twice, if you will.
So this requires realizing the basis of the free group, which if you go to a more general group sounds horrible.
That's true. So to correct, we'll subtract off the entropy of the random variable.
Minus 1 times.
Yeah, just minus 1, just because we have only 2 directions. If we had more, we would put r minus 1 where r is the rank. Okay, so this might not work. I mean, we need to do a little bit more. So we want to take W. So remember, W is a finite subset. And, well, yeah, I guess this certainly works. We can take the infimum over all W. And this is what I'll call the, I've been calling it the F invariant, which is not a very good name, but it's the name that's has stuck. Another way of writing this, by the way, this turns out to be equal, you might wonder, is as taking the limit as r tends to infinity and just putting the ball of radius r here. Ball of radius r with respect to the word metric. So, yes, which again depends on the choice. But as it turns out, that this is an invariant, and it does not depend on the choice of generating set. So theorem due to myself. So this is a measure conjugacy invariant. It classifies Bernoulli shifts in the following sense. Well,
we definitely in the free group, right?
Yes. Yeah, just the free group.
Anyway, that generalized anyway.
Yes. Yeah. Yes, if you want to consider rank R, then you're going to put in R minus 1 here. And you can even consider infinite rank if you rewrite this as a sum. Okay, well, I made one little, I forgot to say, you want to choose phi to be a generating partition. So the definition, yeah, I didn't actually write it down, so maybe I'll write it here, because this isn't necessary now. So we define the F invariant of the action to be the F invariant of phi, where phi is any generating function. Generating means that if we look at the sigma algebra that makes phi measurable and is also gamma invariant, so the smallest such sigma algebra, that should be the entire sigma algebra of measurable sets up to measure 0. Okay. Okay, so this is a measure conjugacy invariant, and so it doesn't depend on the choice of generating observable or generating function. For Bernoulli shifts, it gives you the correct answer, just the base space. For Markov chains, so in the case of Markov chains, it turns out to be a finite computation. That it, you don't have to consider this W. So this is so we can compute it exactly. So I'd like to give you one example, which is a kind of, which is related to the Ising model in statistical physics. So this example will show where, by the way, this proof can be proven just by computation, but I want to explain another way of deriving it. Another way which is more intuitive and tells you a lot more.
So I guess, is there a way saying that it's not zero and infinity only, that you get non-trivial things just by looking at is there a intuitive way of seeing that?
Yes. At this stage, I don't think it's very intuitive, at least not for me. Once you know that it's true for Markov chains, then of course, but yeah. I'll give you a more intuitive picture in a moment. Okay, so I'll describe the Ising model, a Markov chain related to the Ising model very quickly. And this is the diagram. What it means is the following. So what I want to describe here is a random function from my free group into -1 + 1. And the random function is defined like as follows. First, we just flip a coin for the identity. Maybe this is a +1. Then whenever we cross an edge, with probability epsilon, we will flip the sign. So maybe this will go into a -1. And with probability 1 minus epsilon, we keep the same sign. And we just keep doing this. So we just keep moving outward from the center. So that defines a random function. And it turns out that its law is invariant under the action of gamma. And it's a Markov chain. It's defined in that way. So we can compute the F invariant precisely. So the F invariant I'll write down the exact formula. Okay, so it's a nice continuous function. The interesting case, or one interesting case, is what happens when epsilon equals 0. Okay, when epsilon equals 0, there's no transitions. So it's either +1 or it's all -1s. And this term goes away, this term goes away, and we just have minus log 2. And I guess I erased it, but this is really good for the, okay, never mind, I'll tell you that later. I don't want to get ahead. Okay, so what I want to do now is explain to you a different way of viewing this, which will explain why you get minus log 2. You want to know why is it that we can get a negative number? And it will also maybe shed some light on the Ornstein-Weiss example. Okay, and for that I need to go back to the integers first, and then I'll explain it for the free group. So I want to, for the third time, I guess, explain entropy for the integers, but from a very different point of view. Okay, so again, we have an automorphism and a random variable. and I want to say what's the entropy. And what I'm going to do is I'm going to approximate the integers by a discrete circle. Okay, so instead of thinking about, well, I want to think of this system, but I want to look at a finite model of it. And so what does that really mean? I say that a map on my discrete circle into A, I want this map to be a good approximation to my map phi in some sense, or my random variable. So I'll say that it's W epsilon good, where W is a finite subset of the integers. Epsilon is positive. If the following is true. Well, the intuition is that the local statistics of this should be like the local statistics of a typical orbit. If you look at a typical orbit of X, and then you hit it with this map phi. Okay, so what it means is that, well, you could write it this way. So we let X and X be random. The law of it will be mu, or the probability distribution. And we also let V and Z mod NZ be random, and this is just going to be uniform. Then we consider the map, which takes an element W in this finite set, to psi of V plus W. Okay, so this is some random map on W. We consider its law, and we compare that to the law of the map which sends W, again in capital W, to phi of TWX. Okay, and we want these two laws to be close. This law, by the way, maybe I should say this law is a probability measure on A to the W. It's just maps from W into A. And since A and W are both finite sets, this is finite. So this is just saying that the local distributions are close. Okay. Okay, finally, what's the entropy rate? This is well, we count the number of W epsilon good maps from Z mod NZ into A. And we expect that this number is going to be growing exponentially. So we take its logarithm and we divide by n. And we take the lim sup, or maybe the lim inf. It doesn't actually matter which one you take here. You get the same answer. And then, well, we want our approximations to be getting better and better, so take the infimum over epsilon and W. Are there any questions about that? This is kind of a main point. Okay, well, so we do something very similar for free groups. Okay, so for free groups now. So now we're back to the free group. And, always the same setup.
And it's obviously the same.
Is it obviously the same? Okay.
Yeah, it's like, it should be, I guess, but that way.
Well, I should say some words. If you want to count, think of W, just to be easy. Think of W as just, 0 and 1. So we're just looking at what percentage of the vertices are colored a particular color, and also nearest neighbors. Then, so that's kind of an easy computation. You can, it's not difficult to get an exact, just combinatorial formula in terms of factorials, and then you use Stirling's formula, and this pops out.
Soup, you can just write limit there. Since you said lim soup and limit are the same thing.
Well, after you take the enthemum, they're the same. I'm not sure that the limit exists. Yeah, it's a little too.
Sorry, entropy of phi. You want to get the entropy of.
Yes. Yes.
You have to get into somehow some of this mu log.
What I probably should have done is said, the notion of good map here depends on this phi, because we're saying that the local statistics of psi is close to the local statistics of phi. Okay. Okay, so the idea for the free group will be the same. We need some kind of finite model for the free group. And, we'll have the same notion, basically the same notion of a good map. Okay, so I'm going to let sigma n be a homomorphism from the free group into the symmetric group on n things. And intuitively, what this is doing for you is you have you get a nice graph on the set 1 through n, where you put an edge labeled A if, maybe I should put I here. If sigma n of A at I goes to, well, let's call this J just for the heck of it, goes to J. And you'll also have, arrows labeled B. And so you'll get, so if you have a homomorphism, then you get a graph where the edges are directed and they're labeled A and B. That just kind of provides some intuition, although it's not, logically necessary for what I'm going to say. Okay, so a map from now the vertex set, so that's the set 1 through n, into my alphabet is W epsilon phi, and I guess it also depends on this homomorphism. So it's good if, well, it's the same formula, so we look at the map that sends a W to psi of sigma n v, sorry, this should be a W. V is, again, uniformly at random among all the vertices here. We want the law of this to be close to the law of...
You want the kernel of this, you want the sort of, I guess, the mini Schramm feature that you want in this quotient. I mean, you could have taken other quotients, right?
Yes, so I haven't yet told you anything about this homomorphism. I'm just saving that for later. We will have to make some choices. Okay. Yeah, there are a lot of homomorphisms. Okay. So the idea now is that we count the number of W epsilon phi sigma n good maps. And we look at the exponential rate of growth. Let me leave some space. So we'll divide by n, take lim sup and infimum. And this is a good idea. So it turns out that the F invariant does pop out of this, but I haven't told you yet how to choose the sigma n's. Okay. So as sigma n is just a homomorphism. So the idea is we'll just choose these uniformly at random. Now, the number of homomorphisms.
You take the generators to random elements in the group.
Right. Yeah. Right. There are n factorial squared homomorphisms. Because you have n factorial choices for each generator, and these are independent because you have no relators. So we just take sigma n at random, and then we'll take the expected number here. And it's important that we put the expectation here instead of before the logarithm. You know, I mean, we're taking the expectation first and then the logarithm. Okay, so now this should explain, at least in part, why.
I mean, the intuition is that the random, if you took the guy to the generators of your free group to the random elements there, that would work, probably. Right? That's what you really want to do.
You mean you want to switch?
No, I don't want to switch. I'm just saying that the intuition is the random guy. He's mapping the free group. I mean, you're trying to somehow count on this group and make some definition. And that's the trouble with the free group is how do you, with Z, we go 1 to n always.
Yeah, right, yeah.
Group, you don't have, there's always the same measure, but yeah.
Yeah, we don't have any natural quotients.
Right.
There's no reason to prefer any quotient over any other one.
Right.
Okay, so.
Good thing you got some kind of questions.
Okay, so we have gamma now acting on, say, 0, 1 trivially. I told you before that that's minus log 2. That's what we got for the Ising model. And what this means, well, okay, why is it negative? Well, that's the reason why is because typically there's no good maps. Okay, so we're getting, you know, what it's saying is that this expectation is about 2 to the minus n. And why is it 2 to the minus n? Well, if you take one of these homomorphisms at random, you get this graph, as I erased, and you ask, well, can we divide it into 2 roughly equal parts, color half of them 0, half of them 1, very few edges in between? The probability that we can do that is about 2 to the minus n. So it's very small. That's what this says. Okay, so I'd like to explain one more thing.
Macro case is also the same number.
So
We have also just negative numbers in that case too.
oh, we can get negative numbers. We can also get positive numbers. I guess I've erased the Ising model, but so I wrote down this explicit formula for the F invariant for the Ising model, and oh, it's still up there. So when epsilon is a half, this is just log 2. So it's going to be positive, you know, when you're just, you know, Bernoulli. But when you're, when the transition probability is very small, but it can still be positive, so it can still be a mixing Markov chain. It can be very small but positive, and this will be a negative number.
But if you have, I think, model with the interaction on 2 steps.
Okay.
Do you have the same effect?
I assume yes, but I don't have any I can't tell you anything off the top of my head. I mean, if just a two-step Markov chain, you should still get negative F invariant as long as the transition probabilities are small enough.
Does getting 0 for this F invariant mean anything in particular?
Yeah, you know, it's a kind of a good question. I don't really understand it, and this is a big open problem to understand, in some sense, how concentrated this is. I mean, this is, you know, it does concentrate, but you know, let me put it this way.
Yeah, like a Shannon, what's it, prime? It's a theorem which says that the entropy can be measured in terms of almost all forms.
Oh, sure, Shannon-Macmillan, yeah.
That's true, yeah? In your theory?
Well, there is no Shannon-Macmillan theorem yet. At least we don't even know what an appropriate statement would be. Because we have to go outside of the system. We're not actually looking at orbits. We have to go outside of the system to do a computation. So it's not even clear what a reasonable statement is. Okay. All of this generalizes to arbitrary sofic groups. So in the last 5 minutes, I want to explain that. So this includes like all linear groups.
So far, you've just introduced your entropy, shown it's from the definition that it's invariant under conjugation or under isomorphism. You didn't discuss, which I think you mentioned in a previous theorem, the converse, that these are decisive. Is that some of that's true here?
Yes, that is true. It's certainly true for the free group. The F invariants, yes.
Entropy.
Yes.
I mean, the Bernoulli is determined
yes.
by the entropy.
It's true. It's basically true for all groups modulo a very small potential counterexample, which we don't know about. It's the topic of Monday's talk, or at least part of Monday's talk.
Okay. So that certainly sells your entropy.
Yeah, sure.
If it's a totally invariant,
yeah.
I don't care what it is.
It's a total. So, for example, for all linear groups, it's a total invariant. Yeah.
But the choice of Sn was kind of.
Yeah. So yeah, we still don't know your definition. Right now, it seems to depend on.
And so you could have chosen instead of Sn some other
Finite
sort
groups.
of nice finite groups and all the maps from gamma to that, and then make
So
that.
suppose you have a sofic group.
Yes.
You have a sofic group.
Yes.
Those are residually finite, I guess. Are they? I don't know.
No. Residually finite groups are sofic, but not necessarily the other way around. So to be a sofic group means that there exists a sequence.
Right. And then things depend on the sequence.
These are just set, right. These are just set maps. They don't have to be homomorphisms. Right.
So then how does your Ornstein theorem read?
Oh, well, it turns out that for Bernoulli shifts, the entropy does not depend on the choice of sofic approximation.
So even for the free group, instead of the sequence S1, S2, S3, Sn, you could have replaced that by another sequence of groups, right, finite groups, and taken the sequence of maps from the free group into that, and
Yes.
you would get the same thing?
That's
Sn just.
That's absolutely right. We would get the same thing for Bernoulli shifts. In general, the answer is no. We don't get the same thing. But if you exclude the value of minus infinity, it turns out that we might get the same thing. That's a conjecture.
Okay.
Yeah.
But for Bernoulli, these are canonical notions.
Yes. For Bernoulli, you always get the same thing. So here I'm just rewriting the definition of a sofic group.
Yeah.
So your group is sofic if there exists a sequence of maps. These just have to be set maps, not necessarily homomorphisms. But from gamma into the symmetric group on some finite set. Vn. And they have to be asymptotically homomorphisms, which is what this means. So, and they should be asymptotically free. And then we can define the entropy with respect, of an action. And here we'll have a random variable in this way. And I've just erased the expectation because we don't, it's not random anymore. So this turns out to be a good definition. It is a measure conjugacy invariant. If we give phi if phi is a generating function, so it generates the sigma algebra together with the group action, then this does not depend on the choice of phi. It's just, and for Bernoulli shifts, it gives you the correct answer. It gives you the entropy of the base. Okay. Of course, you could choose your phi n's to be random and put an expectation here, and you would get, possibly a different invariant. So we have large families of invariants and lots of open problems. Okay.
Entropy, everything's entropy. Any questions?
Can you say something about how we can calculate these formulas, why they distinguish different from Bernoulli's, or how would you calculate one of these things?
Oh, sure.
Do you get something about the root maps, sort of saying that the root maps are in a certain way?
Well, in just about all proofs of computations of sofic entropy, the proof splits into two parts, proving a lower bound and an upper bound. And this is very interesting, actually. There's a good reason for this, I think. Anyway, the lower bound, you want to show that there's a lot of good maps. Okay, how do you do that? Well, you just, for the Bernoulli shift, you just choose them at random. And then you show that the typical random map is a good map. Yeah, and so it basically boils down to the law of large numbers. It's not a terribly difficult thing. For the upper bound, well, you say, well, if you have a, well, for the upper bound, yeah, okay. It follows almost immediately from the definition that this is bounded by the entropy of phi. You can see that already if you just replace W here with the identity. Because a good map, right, has to have the same percentage of colors. And that's exactly what this entropy is giving you already.
So the second question she asked, I think, was the Ornstein side of things. Why that seems...
yeah. Well, I mean, I could say some things now. I mean, or I could wait till next talk.
Oh, yeah. Find that next time.
Yeah.
Any other questions? Okay, well, you all have a weekend to rest. But you here Monday afternoon. Let's next week again.